Welcome to the third video in this spacetime algebra series. In this, we're going to be going over the relative frames. So first, let's consider this fact. The sub-even algebra, denoted STA plus, that looks more like a dagger, I'll write a plus, is isomorphic to the algebra of physical space, which we've covered. Now this algebra of physical space is defined as G3, which is just an extension of the real numbers, where you have sigma x, sigma y, sigma z as the basis vectors here. So this isomorphism, say, this isomorphism is a result of choosing a specific inertial reference frame. A specific inertial reference frame. So I'll show what the mapping is between the basis vectors here, and then I'll talk about cross products and space-time splits between paravectors and vectors and bivectors and biparavectors within these two algebras. So you get that's the wrong one. You get vectors and bivectors here, which map to paravectors and biparavectors respectively in the APS. So the standard mapping, oh, that's bad. The standard mapping is generated by this right here. I'll write it gamma j naught maps to sigma j, where again this sigma is one of these basis vectors. So you have a bivector here mapping to a vector in the algebra of physical space. So this results in the following mapping. You end up with 1 there. You have gamma 1 naught, gamma 2 naught, gamma 3 naught, and then gamma 1 2, gamma 2 3, gamma 3 1, gamma 0 1 2 3. And I only included even elements here because we're looking at the even subalgebra of this space of the STA. So this, don't want to convert that, I just want to copy. And move this one up. So these map to, within the algebra of physical space, this just maps to 1, sigma x, sigma y, sigma z. Now, what does 1, 2 map if these are the mappings here? Well, if you have gamma 1, or if you have gamma 1 0, 0 2, then this is equal to gamma 1 2. So that's what these are equal to. But that's just gamma 1 0, negative gamma 2 0. So this, if you map these both individually to their respective basis vectors in the APS, you end up with this mapping where you get sigma x minus sigma y. So minus sigma xy. and that is the mapping for this. You end up with an almost identical one here, minus sigma yz minus sigma zx. And then this very similar thing happens. You end up with sigma x, y, z. And to kind of highlight some of the complex structure that we have in the space-time algebra, we also have a similar thing in the algebra of physical space. If you recall from other videos, where this right here is actually equal to negative sigma z I, where I is the pseudoscalar of the algebra of physical space. So you actually end up with a complex, system even in the algebra of physical space, where recall this gamma 1 2 is equal to negative gamma 3 0 I, where this I is the pseudoscalar here. So you have that complex behavior even in the algebra of physical space, which is why it's able to describe relativity. Now let's look at the bivector cross product. So if we have f and g in the 2 grade subspace, then that means they are bivectors. So if you have that, then their cross product, if you recall, was defined as f cross g, which is equal to 1/2 fg minus gf I inverse. Well, this here implies, this stuff implies that gamma j naught cross gamma k naught, so these are just different bivectors, different bivector bases up here. Then the cross is gamma, it gives you another one, gamma L naught. So an example of this is like 1 2 or 1 naught, 2 naught, gamma 3 naught. Well, if you look at the mapping here, this will map to, I'll write this in pink, use sigma j cross sigma k is equal to sigma L. Well, this just implies that for a vector v in the algebra of physical space and a vector w in the algebra of physical space, their cross product is 1 over 2. And then you have v w minus w v. Then the inverse of this, just all of this is a result of this mapping from here down to here and from here to here. And if we simplify this, there's the identity. If you recall, if you have a cross or a, if you have a wedge b in the algebra of physical space, that's the same as a cross b times I. All of this times I. So there's this identity that we will use. And that means that this is v wedge w. And then the inverse of I is negative I. So we end up with this result right here. V wedge W is equal to V cross W I. So through this mapping, we're able to reconstruct an already known identity of the algebra of physical space. So that's more proof that this indeed maps to the algebra of physical space and allows for that structure to exist, or that's it's more of a structure of relativity than it is the algebra of physical space. It's pulling it in from the space-time algebra because it's isomorphic to the space-time algebra's even subalgebra. Now, one more thing to consider. So let's also just can do this as a little side thing. We consider the electromagnetic field. So I'll say this electromagnetic field, which would be F equals E plus BI. So this is an electromagnetic field in the algebra or in the space-time algebra. So this right here is in the STA, but it's technically plus. Well, if we just do the mapping, we map to the APS, end up with F is equal to, or this F is equal to the sum through J of all EJ, and then you have gamma J naught plus B that's sub J gamma KL. Well, if you then map this out, you end up with the sum through J of EJ sigma J plus B sub J times sigma KL, where this is a biparavector. So you have a vector component and a bivector component. So this indeed ends up with F in the APS, and specifically the 1 plus 2 because it's a biparavector. So you can see that this mapping from the space-time algebra to the algebra of physical space also makes sense. So now let's consider some space-time splits. So you have a space-time split. You have one for paravector, or for vectors to paravectors. So this is vectors to paravectors. Let me just do this for clarity. And then here you get bivectors to biparavectors. So if you have some vector in A, or so you have this in the STA, where A is equal to AT plus the sum, or this would be AT gamma naught plus the sum over J of AJ sigma, or that's not sigma, that's supposed to be gamma J. Then A naught, or A gamma naught maps to this A being equal to AT, or AT plus the sum over J of aj sigma j. Because this, when you multiply by gamma here, this gamma naught becomes 1 because gamma naught squared is 1. But then the gamma naught multiplied on the left right hand side of this just maps to these right here. So you end up with a paravector. And likewise, if you have a bivector in the STA, then you have that f is equal to f gamma naught squared, right? Because it's equal to 1 times f gamma naught, which is equal to f dot gamma naught, plus f wedge gamma naught. And this gamma naught right here, dotted with a bivector, this is going to give a vector. So it's going to give gamma sub j components, which then multiplied by this will map to sigma j's. So this will map to, this implies that f maps to f equal, you end up with the sigma components here. So you end up with f j sigma j plus, and this right here creates a trivector, which then becomes this gamma naught gets rid of the bivector component, or sorry, not the bivector component, gets rid of the time component in this trivector, making it one of these bivectors that'll map to one of these. So you end up with this right here with a minus f, or then this would be a KL sigma KL. And this would be your space-time split for the bivector to a biparavector. So this ends up being in the algebra of physical space, just as this one does right here. And that is how the algebra of physical space is related to the space-time algebra.